We're going to continue with chapter 8. I know I ended up on this slide, but I didn't get through it, so I thought I'd go through it again. So when we're talking about a soluble ionic compound, that means when I add it to a solvent, and again, usually it's liquid, a liquid or water, which is most of the time a liquid, you get this interaction between the salts, remember, become ionic, and the water has that polar, so you get ion dipoles forces, and they're very strong, and they'll overcome and break it down into your ions, so then you'll get, they'll be very soluble. But not all ionic compounds, it depends on the size of them and stuff, will be soluble. And some of them will have limits to their solubility. So it just depends. Excuse me. Anyway, so for a soluble ionic compound, there is a limit. You can't just dump and dump and dump. If you look down here, okay, I have the same amount of solvent, water. Let's say I'm adding a salt. See this one where it's all dissolved? This is called an unsaturated solution, which means I can add more to it and it'll still dissolve. But I keep dissolving and adding, I shouldn't say dissolving, I keep adding, and eventually it won't dissolve anymore. There's limits for all the ionic compounds, and some of them can dissolve a lot. Some of them can't, okay? It just depends on the compound. But you can see after a while you add it, it doesn't dissolve. So now I've made a saturated solution. It's dissolved all it can. Now you can do some things to change solubility. You can increase the pressure. One of the most common things is to increase the temperature. When you increase the temperature, you increase the solubility. In other words, it'll dissolve much more, okay? So when you're looking at solutions, if you form ions, there's an easy way to tell if it forms ions. All you have to do is you can put like one of those little meters that have the little light. If the light goes on, that means you have ions, and that solution is called an electrolyte. And you can see I have an example, Pedialyte. Okay, when you get sick, especially little kids, they need to replace their electrolytes. And electrolytes are basically ions. Calcium, sodium, potassium, chlorine, iodine, things like that. You have these ions in your blood, they're cruising around, and they help with various things. They help your body conduct things and so on. You're basically a huge conductor because you have to conduct your nerve impulses. If your nerve impulses don't go where they go, if they don't get where they're supposed to go, then you're in trouble. And that's when you get super dehydrated, you get cramps and stuff, because the information isn't getting where it's supposed to, because you don't have the electrolytes to push it through. So when you get dehydrated, it's not just water that you need. You need to replace your electrolytes. You need to replace your ions. And that's what sports drinks do. Gatorade, Powerade, all those guys. What they do is, besides just water, they give you these electrolytes. And your electrolytes are actually regulated by your hormones, okay? So it took them a while. I don't think it was till 1969 that Gatorade was invented at the University of Florida, the Gators, that they realized when you're getting dehydrated, it's not just water you need. Because when you sweat, you lose a lot of other things too. So then they started putting electrolytes in it. And the other way you can tell that they kind of work is if you've ever been really hot and sweaty and you drink a sports drink, it tastes a lot better than if you just drink one when you're not hot and sweaty. They taste kind of salty when you're not in need of the electrolytes, but when you are, they're like, they taste wonderful. Maybe that's just me, I don't know. But again, electrolytes are important in other ways too. We have electrolytes in your car battery. You have sulfuric acid that's dissolved in water, and it's a wonderful electrolyte, which is really good because you need to conduct electricity through that battery, otherwise your car doesn't start. Okay, so if you lose your electrolytes, it's very important that you replenish them. You're going to have issues because of it. Okay, and again, it's not just water that you need. If you're really dehydrated, you need other things too. Okay, why do we get these electrolytes? Okay, here's an example of a covalent compound. Okay, it is nonpolar. So if you look right here, the water tries to get in there, but it's not attracted to the water because the water has a positive end and a negative end. Since there's no positive and negative ends in this molecule here, it's covalently bonded evenly, it won't pull it apart because there is no positive and negative ends, okay? In an ionic compound or a polar compound, you have negative and positive ends, so the water's attracted to them, so it can, use that to pull these apart. So whenever you have a nonpolar substance and you try to dissolve it in water, it won't dissolve. And again, remember, likes dissolve likes. Water is polar. This is nonpolar. They won't dissolve each other. Okay, so solutions with dissolved molecules, they're called non-electrolytes. There is nothing to conduct electricity. You don't have ions with their positive and negative charges. Okay, so again, we talked about likes dissolve likes. Nonpolar solutes will only dissolve in nonpolar solvents. Okay, and I talked about that a little bit. If you get a grease stain, grease is nonpolar. You ever do that? Get it on your favorite shirt, and then when you wash it, it's still there. If that happens, you guys, if you buy butane, the stuff that it comes in a yellow bottle, it's what they use in Zippo lighters. Butane is an organic substance. It's a fuel, and it's nonpolar. So if you spray a little bit, put that on your grease stain and then wash it right away. Don't let it sit. It'll take the grease out. Okay, that's my Martha Stewart hint for the day. I guess she's more of a cooker, but got to give you some laundry tips. Anyway, and the reason why it works is because the likes dissolve likes. Likes are attracted to each other. You don't have those electrolytes. You don't have those other charges. You have weak dispersion forces and a little bit of dipole, but not much. So that's why it would work. Again, likes dissolve likes. And if you're looking at the ones that are nonpolar, it's usually the hydrocarbons with five or more carbon atoms. Okay, this one only has 2, but hydrocarbons with 5 or more atoms are common nonpolar solvents. Butane has 4. I guess it's not a common solvent that you use, but it really does work when you're trying to get grease out of your clothes. Okay. Dry cleaning solvents are an example of nonpolar solvents. They dissolve dirt and grease without water. Okay. And the most common here is tetracycline. We got tetra for 4-chlorine. Tetrachloroethylene, but they call it tetracycline. Anyway, tetra, 4-chlorine, chloral, and then ethylene, because 2, double bond. I know, it was the last chapter, but it's got to stay with you because you still got that final a ways away, but And the other thing about it is non-flammable. Okay, so again, when you're talking about dissolving stains that are nonpolar, like grease, let's face it, that's a common thing that we do, then you need to use substances that are nonpolar to get rid of them. Okay, a lot of those stain sticks and everything you do, same kind of deal. But I'm telling you, Zippo fuel butane works really well. Okay, so here is what they call a solubility curve, and I wanted to talk about that because that's what your assignment's going to be today. Okay, for most solids, as you increase the temperature, you can increase the solubility. In other words, more will dissolve. All right, it's not always true though. And some, like this one, cesium sulfate, actually decreases. That's rare because you can see there's only one of them. Most of them increase as you increase the temperature. Here's salt, like I was telling you, temperature doesn't really affect salt much. It's pretty much straight across. But if you want to figure it out, okay, so let's say I am making a solution of, here we have potassium nitrate, this green line. Okay, and I have 40 grams. Excuse me, and I want to know what temperature I have to heat my water to so that my 40 grams dissolves. Here's 40 grams. I go until I hit the line, and then I go down, and it's about 25. So 25 the temperature needs to be 25 degrees, and then my 40 grams of potassium nitrate will dissolve. Okay, up until this point, so from 0 to 40 grams at 25 degrees, my solution is unsaturated. I can add more and it'll dissolve. Once I get above that level, so here I'm at 25 degrees, okay, I've reached my 40 grams. It's about there, yeah. Okay, so here's my 40 grams. If I add, the water's still 25 degrees. If I add more than 40 grams, now my solution is saturated. It's not going to dissolve it, okay? If I add more and I still want to dissolve, let's say I have 60 grams, okay. So I go 60 and I go over to where it hits it right here, okay? And then I go down, I got to warm my water up. I got to heat the water up to 40 degrees, okay? And then again, I'd have a saturated solution. Below that point, below 60 grams, it's unsaturated. Above it, it's saturated. So that's how you use a chart. So let's say I add 100 grams of lead nitrate. Okay, I'm adding 100. And this over here, this is 100 grams of water. So let's say I do 100 grams of lead nitrate and 100 grams of water, and the temperature is 30. Do I have a saturated or unsaturated solution? Okay, here's 30, the temperature, and at that temperature I can dissolve, about 65 grams. I said I'm adding 100. So I definitely have a saturated solution. Actually, only the 65 will dissolve. The other 35 are wasted. They're just sitting on the bottom. Okay, so that's how you read a chart like this. Okay, so this is a solubility curve. It was experimentally, they did made a curve like this by actually measuring how much dissolves in certain temperatures. But you can use this chart. Now, one thing down here, the gases are totally different. Okay, all gases, as temperature increases, sorry, I'm covering this up, solubility decreases. Okay, and again, the reason for that, remember, gas particles move really, 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 really fast. So if you increase the temperature, they're going to move faster, and if they move faster, they're going to escape. Okay, they're not going to stay in solution. So the colder they are, the more the gas particles stay in solution. And think about that with pop. Warm pop has less fizz than cold pop. As soon as you open up that top, those gases escape. The colder it is, the more they stay in solution because they're not moving around as fast. Okay, when is that really important? For fish. Okay, here's oxygen. All right, as you increase the temperature, you lose your gas particles. Okay, so you want the water, look at here, oxygen's best when the water is about 4 degrees. Fish like the water to be cold. Okay, there was one thing for a while, people were dumping, like in power plants, they'd heat up water and they'd use it to conduct electricity, and then they dump the water back in the river. They didn't do anything to it, so they're like, all we did was add a little heat to it. Shouldn't be a problem. It is a problem because that water heats it up and then you lose the oxygen. And so they're like, why are the fish dying? Well, there's no oxygen in that water. So now if you look at power plants, they have big cooling towers that they let the water sit in and cool before they release it back. Took them a little while to figure that out. But cold water has much more gases, especially oxygen dissolved in it. As you heat it up, you lose the gas particles because they start moving around too fast and they escape. That's why all gases decrease solubility. Here, helium, because it's a noble gas, it doesn't change much, but you can see these other guys change quite a bit as you increase the temperature. So cold water is best for anything that lives in the water that needs oxygen. Okay? Okay, so that's where we're going to quit today, and then we'll start talking about concentrations. But your assignment today is going to deal with a graph like this, so that's why I thought I better go through it. All right? So that's it for this. Next, we're going to work on concentrations.